My name is Corey Kramer. I'm a graduate student in the civil engineering department. Specifically, I work in geotechnical engineering. So the goal of our research is basically there's two main components. The first component deals mostly with the energy and the efficiency of the system. The second deals more with the geotechnical concerns. The system we're looking at specifically are energy piles. Now basically what that is to support a building, now considering just the foundation elements, there's two general types. There's shallow foundations and deep foundations. Shallow foundations are typically footings and things like that. They're several feet below ground. They're not particularly deep. On the other hand, you have deep foundations. That's typically piles. If you consider a concrete pile, it's basically a long concrete column that supports the building load. These are basically designed so they can carry a building using some frictional forces along the side of the piles and some resistance under the base of the pile. A current method that's actually used often in residences that have geothermal systems, they actually just lay the coils in the soil at some shallow depth. The fluid's allowed to circulate through the tubing, and heat exchange occurs through the tubing and into the soil. Now, saturated soil has orders of magnitude higher heat capacity and thermal conductivity, which again makes it much more efficient than exchanging heat with air. The soil used in this experiment is an Ottawa sand. It's a very typical laboratory test sand. It's over 99.9% pure quartz silica dioxide. The reason we use this is because chemically and mineralogically it's very uniform. In terms of grain size and grain shape, it's also very uniform, and it basically allows us to create some type of an idealized situation rather than going to some natural, very well graded sand. To better understand the behavior of energy piles, basically we made a laboratory scale energy pile that's very well instrumented and very well controlled, that we can really start to understand some of these fundamental behaviors. So regarding the energy efficiency and kind of the heat flow behavior of this system, similar to how they construct them in the field, we embedded some PVC tubing in the concrete, and that's going to allow us to circulate the fluid as it would be coming from a heat pump inside the building. The way we simulate the heat pump is actually we have a temperature controlled water bath. So that's what this is right here. What this allows us to do is this simulates the thermal loads from the building. So essentially, if we want to simulate what the ground would be experiencing on a hot summer day, the ground is going to be some kind of neutral temperature year-round, somewhere around 50-60 degrees, particularly when you get below, several feet below ground. That temperature is constant, both daytime and nighttime, as well as seasonally. The temperature is very mild and very constant. When it's hot outside, you actually have these very elevated air temperatures, and you want to cool the building down, so all of that heat, that thermal load, is actually going to be transferred into the ground. That's what this temperature bath allows us to do. So not only can we set the temperature of the circulating fluid, we can also set the flow rate, and more importantly, the velocity. Those are two very important design parameters. So basically, what this data allows us to do is, it allows us to study the heat flow behavior from the pile to the surrounding soil system. One parameter in particular is kind of looking at this zone of influence of the pile. So basically that's at what radial distance does the soil feel some increase in temperature. That's important because oftentimes piles are not installed by themselves. They can be, but oftentimes they're installed in pile groups. There's some speculation of if you have multiple piles near each other and their zones of influence cross each other, does that somehow affect the efficiency of the pile? This will somehow allow us to quantify, what is that zone of influence initially, what is it with time, does it ever reach a steady state, these kinds of behaviors. So again, we can try and really understand this behavior, and this will lead almost directly into some kind of design parameters. Given your pile geometry, given the what you're trying to heat or cool the building to the outside temperature, all these kinds of things. You want to make sure that your system is being as efficient as possible. The parameters that we're concerned with particularly are when we're circulating this fluid, what kind of temperature difference between the soil and the fluid should we be looking at? How quickly should we be circulating it? All these kinds of things. And that's kind of what we're looking at for the energy side of the research.